In this video, we're going to go through some definite integrals, interpreting them as areas under curves. We're going to think about definite integrals as signed areas. So here are the problems we're going to look at in this order. The first one is we need to graph the function f of x is equal to 5. There it is. And we need to look for x values between 2 and 12. That ends up becoming this rectangle. The width of this rectangle is 10 because that's from 2 here to 12 there. And the height is 5. So area of a rectangle, just multiply, you get 50. The next example is f of x equals 5x. So that's a line of slope 5 through the origin. And the scaling on this is a little off just so that you can see what's going on. And we need to look again for x between 2 and 12. So that's the region we're looking at. There's two ways to break down this region and compute an area. The first is to break this into a rectangle, or rather it looks like a rectangle, though this is actually a square with the 10, height 10. The area of this square really, and then the area of this triangle above. So this orange triangle has a width of 10, that's there, and a height of 50 because that's from the 10 here to the 60 there. So then we use the area formula for triangle 1/2 times base times height. You add this all together and you'll get 350 square units for the area. The other way to compute this area, this purple region, is to think of this as the area of this big triangle here, which has a width of 12 because that's from the origin all the way up to the 12 right there, and height of 60 because that's from this y equals 0 all the way up to this y equals 60. But that's too big. We've got to now cut out this little triangle right here. So this orange triangle, we subtract away that area. That's 1/2 times a width of 2 times a height of 10, and you'll still get the same number, 350, if you do that. The next integral is we're going to graph f of x is equal to -2. There it is. And we'll look from x equals 4 to x equals 10. So that's this rectangle, although we have to think of this rectangle as being negative area because this is under the x-axis. So there's that minus sign for that reason. Otherwise, we have a width of 6 from the x equals 4 to x equals 10, and a height of 2, so a total area of -12 if we think of the area as being signed. In the next example, we're looking at the graph of y equals -2x plus 6, which is shown right there. We got to look from x equals 1 to x equals 4. So there's actually two regions here shown in gray. There's one positive region here, and then one negative region over there. So then the area of this positive region is 1/2 times a width of 2 times a height of 4, minus due to this negative region. Okay, so we're going to subtract off the area of this region below the x-axis, width of 1, that's right there, and a height of 2. So all in all, you get a total area, a total signed area of 3. The next example is quite similar. We're going to look at the graph of y is equal to 2x minus 4. From x equals 1 to x equals 6, there's two regions. There's one negative region right here and one positive region there. I went ahead and computed the area of the positive region using the area formula for a triangle, width of 1, 2, 3, 4, and a height of 8 along there. And this negative area triangle has a width of 1 right along there and a height of 2. So you get a total area of 15. And the next example is actually the previous example's function. So this curve in blue right along here, it's just now we have to take any part where y is negative and flip. We have to reflect across the x-axis because of the absolute value. So you get a graph that looks like this V shape. So there's a part that's sloped 2 here and a part that's sloped -2. We're still going to look from x between 1 and 6. So as far as the geometry goes, very similar to the previous example. It's just that both regions, both the orange and the green region, we're going to think of as being positive areas. So the calculations themselves, we've basically done this positive area right here for this positive green triangle. That's already been computed. It's just the earlier red triangle, excuse me, that was down there, we're now considering as a positive area. So when you add these, now you get 17. The last example, we need to think of the graph of y is equal to square root of 25 minus x squared. Now, this requires a little bit of foresight, but let's take a look at x squared plus y squared equals 25. That is the equation for the circle centered at the origin of radius 5. And if you subtract x squared on both sides and square root both sides, then this is very similar to y is equal to root 25 minus x squared, with the exception of this plus or minus sign. Well, if you ignore the plus or minus sign, then you're talking about positive y values. So this is actually the top half, positive y values, top half of a circle of radius 5. So we graph that here, and then this definite integral is then talking about the area of this orange region, which if you just say that this is, well, half because of a half circle, and then in parentheses here you see the area of a circle, pi r squared, where r is 5, and if you simplify that, the numerator is here the area of the circle, 25 pi, and this 2 in the denominator is from this 1/2.